Oh, sorry about that. Hey guys, F Train here. It's Monday morning. Hope you guys had a good weekend and hope you're keeping busy. A lot of you guys asked me, what am I doing to keep busy and from going stir crazy? Well, you know, a lot of schoolwork. You know, spending time with family, yard work, housework, cleaning, even helping my wife cook a little bit. Although she is the best cook, so kind of hard. I want to stay out of the way as much as possible. Music, reading, connecting with friends, and spend a lot of time with family. Got to spend a lot of time with my daughter, who's back from Germany now. So good to have her back. And anyway, so let's get to the lesson. Everything's on Google Classroom, so just continue to follow that. Let me just share the screen for a second here. All right, there we go. So let me move that down. All right, so today we are going to be answering the question, what is light? Okay. And a number of years ago, one of my students who I wrote a recommendation. She got into MIT. Actually, a couple of years later, she sent me this T-shirt in the mail and said, "Oh, everybody's wearing this T-shirt, and I thought you'd like it." And I did. I should have worn it, but I can't find it, so I'm sure it's in a drawer somewhere. But anyway, we're that T-shirt right there basically are what we call Maxwell's equations, and are the mathematical equations for light. So that is light right there. So what we're going to do, we'll get into it. I'm going to give you an optional video to watch, learn more about Maxwell's equations. But so what we're going to talk about right now, though, is what are light waves. We started the lesson the other day. It was sort of intro, or a review lesson rather, on waves. And the reason we did that is because light is waves. Light are electromagnetic waves. In other words, they are oscillating electric and magnetic fields. Now, I'm going to, I linked this radiating charge link on your Google Classroom. This is a pretty cool little thing that you can look at on what do you call that? Uh-oh. All right, so so you'll notice that this is a positive charge, and as we learned last semester, positive charges radiate an electric field outward in all directions. Okay, but what happens if I actually move that positive charge, right? And I give it a little tug. See what happened? I actually created a pulse. And so we learned about wave pulses yesterday or last week. And so I can create a wave pulse with by moving that charge. Now watch what happens if I then move that in a repeating pattern. And what I need to do is I need to lower the amplitude a bit. Otherwise it's a little hard to see. But if and you can see what's happening here is that you're getting this radiating wave of electric field. So in other words, the electric field is oscillating. And it's a little more complicated. If you want to, learn more about this, I linked a video. But an oscillating electric field, because it's a changing electric field, it produces a magnetic field. We learned that, moving charges produce magnetic fields, and then that changing magnetic fields produce electric fields, electric currents. And so it's sort of like a spiral. It kind of, or not a spiral, but like a circle. You get the changing of one produces the other, and the changing that produces the other. So watch more about this on the link that I gave you if you're interested. So you see here, this is sort of like a oscillating electric field produces an oscillating magnetic field. Okay, and it radiates outward. That field actually radiates outward at the speed of light, which makes sense because that's what light is. Okay. These are Maxwell's equations here. As I mentioned, optional video you can watch if you're interested in learning more about that. Now, visible light is a very small region of the electromagnetic spectrum. Okay, and I'm sure you've run across this at one point or another in your life, but you can see that the electromagnetic spectrum goes from radio waves to microwaves, infrared, visible, ultraviolet, X-rays, gamma rays. And as you can see, visible light in the middle there is just one tiny little portion of the electromagnetic spectrum, okay? So the light as we see, the light that we see is really the same as radio waves and X-rays and gamma rays. It's just that it's at a different frequency, and our eyes happen to be tuned in to see that frequency. We can't see the other frequencies. But if our eyes had a different, composition or tuning factor, we maybe be able to see reflected ultraviolet or X-rays or things like that. Okay. How do we perceive sound waves of different frequencies? You can pause if you want, think about that. But if I speak really low, that's a different frequency than if I speak really high. So our frequency is, the frequency of sound waves is perceived as pitch, okay? Whereas light waves, or at least in the visible portion, we perceive those as different colors, okay? So a little thing for you to think about, and if you want to pause, what type of electromagnetic waves have the longest wavelength? And what type of electromagnetic waves have the greatest frequency? Okay, so if you want to think about that, the wavelength here is going from, if you look on the right side, it's really, really tiny, okay? And on the left side, it's really, really long. So that would be the wavelength, okay, short to long. So radio waves have the longest wavelength. But in terms of frequency, if you look down here, the frequency goes from really low frequency, like 100 hertz, all the way up to 10 to the 20th hertz. Okay, so obviously then gamma rays or gamma photons would have the greatest frequency. Okay, all electromagnetic waves travel at the same speed in a vacuum. Okay, and that speed is 300 million meters per second, or as you probably know it better, 3 times 10 to the 8th meters per second. Now, as we'll learn later, the speed of light in other materials is not the same. Light slows down when it hits other materials like air, glass, etc. Okay. Electromagnetic waves can be represented mathematically. Okay. So if you look here, and generally the way you'll see this, at least on questions, are the variation of the electric field as a function of time or as a function of distance, okay? So the question is, what is the equation for the graph below? Now, you might recognize this immediately from math as a cosine, right? Because if you look at it, for 0, time is 0, you have a maximum value. And we know that the cosine of 0 is the maximum, okay? Now, if you, and in this case, the maximum value of this function is the maximum electric field. So what is the maximum electric field in this case? It looks like it's about 3 volts per meter. And remember, electric field can either be volts per meter or newtons per coulomb. What is the period? All right, so you might want to pause for a second and see if you can figure out what the period is. But if you look at it, an entire wave goes from crest to crest or trough to trough. And you can see that from crest to crest, that's about, looks like 4 seconds, and trough to trough, 4 seconds. So the period is 4 seconds. So we can represent this wave then as an equation. And the general equation for this is E is E max times the cosine 2 pi over period times T. Okay, so which kind of makes sense, because if you think about it, if you put in one period, then it's going to give you a basically it's going to coincide with an angle of 2 pi, and so 2 pi over 2 pi gives you a cosine of 1, right? Okay, so this is the equation for so in this particular graph here, you'll notice that since the period is 4, if I put in 2 pi over 4, that's the same as pi over 2, and E max is 3. So my equation is going to be E is 3 volts per meter times the cosine of pi over 2 times time. So obviously, as time increases from 0 to 1 to 2, the E is going to oscillate up and down, okay? What is the equation for this graph? Notice now that position is the x-axis, and again, we have electric field as the y-axis. By the way, the maximum electric field is also the amplitude of the graph, so you might be familiar with waves having amplitude, so that's the amplitude. So what's the maximum electric field in this case? Well, you can see that it would be 6, okay? Not 12, not 6 to minus 6, but just 0 to 6. So that's 6. Okay. Oops, that should be 6. Let me just change that real quick. Oh, hey guys, after you're back. Sorry about that. I fixed that. So E max now is 6 volts per meter. And what is the wavelength of this wave? So remember, if you want to find the wavelength of a wave, you go from, again, crest to crest or trough to trough. So it looks to me like this wavelength is about 2, right? 2 meters is the wavelength. And so the equation, if it's a function of position, is E max cosine 2 pi over lambda, the wavelength, times x. I should note also that you sometimes will see equations as a function of sine, because it can be sine as well. So obviously, if you see a graph whose value at 0 is a maximum, okay, then that's a cosine graph. If you found a graph whose value is negative at 0, or a minimum, that would be a negative cosine, right? If the value at 0 was 0, then that would be a sine graph. So you can replace that with a sine. It basically works the same way. It's just that it would be shifted over, okay? Okay, so for this graph, you would have, again, E max, which is 6, times the cosine. Now, it's 2 pi divided by lambda, so 2 pi divided by 2 is just pi x, okay? So the graph would be 6 volts per meter times the cosine of pi times x. And so again, as x increases, it's going to go up and down because the cosine varies like that, okay? All right, last thing we're going to talk about here is the fact that we can see objects in 2 different ways, okay? Some objects we can see because they actually emit light. For example, flames emit light, light bulbs, stars, lightning bugs, or whatever. Some things actually produce their own light. A lot of things, pretty much everything else, we see because it reflects light, right? So you can see my shirt, for example, because it reflects light. It reflects orange light around the outside and all colors of light in the middle. Okay, and shout out to my homies on the F train. Anyway, now, so everything else reflects light. So, and the way that it reflects light tells us a lot about how we see it. You know, the different colors of light it reflects, you know, shows us what color that we're going to perceive, and, you know, texture, and, you know, we'll talk about things called diffuse and specular reflection. All right, mirrors reflect all colors, but so does white paper, but you can't look and, you know, see yourself in a piece of white paper. So there's reasons for that. Okay. Um, Now, if you look at this picture here, so you've got all this pencil. Now that one little molecule of pencil is emitting light in all different directions. However, you notice that only a little bundle of those light rays actually is going to hit your eye. And but what's cool about our eyes is they're able to kind of like trace those rays backward, and, you know, determine, you know, where, first of all, what that object looks like, color and things, but also kind of where it's located, because our eyes sort of have an ability to do that. And then especially with two eyes, it's even better. Okay. And the fact that, again, light rays are reflected allows us to form images. Okay, so, you know, if we look in a mirror, we see an image of ourselves. If we look through a lens, we see images of objects. Okay, and so reflection of rays is how images are formed, at least in mirrors. Okay, so we're going to talk more about that next lesson. Hope you have a great day, and I'll talk to you guys very soon. Have a good day.